your introduction. And yes, I'm really happy to present to you the results of a project. The study has been financed by the European Commission and the Intelligent Energy Program, and the project is called Smart Domestic Appliances in Sustainable Energy Systems. So we are close to the end of this project, so the results which you will see on these slides in the next half hour, they are to some extent pre-final, but I think we're quite well through the work program, and I'm happy to show you results of this project. Now, as you can see on this slide here, we have a group of team members in the Smart A project, as we call it, and I hope this is not offending any native speaker of English. The project team consists of researchers and also experts in the energy field, and in also one representative from the energy industry, which is EnBW from Germany, one of the big 4 electricity suppliers and grid operators in Germany, and Miele, which is one of the most advanced appliance manufacturers in Europe. So we have quite a nice group of scientists working on this project. And now let's turn to the overview of this presentation. I would like to guide you a little bit through the vision which was leading our project, and after doing some kind of fancy set out, I would like to go into some more details with you, looking at the demand response options which domestic appliances can give. So it is about load management in electricity systems. The next element would be looking briefly at reactions from consumers about whether they accept and under which conditions the concept of smart appliances. And then I would like to take you through a few slides and figures looking at the economic case of domestic smart appliances, looking into modeling results in 3 steps. I will give you more details later on these 3. And then just quickly a snapshot on an actor analysis which we did, and a quick view on incentives which we might need to get smart appliances going. And then of course some conclusions, and then we're done. Now, what is the vision of the project? And you can see in this picture here that the idea is to connect a household with its appliances to a larger world. So we have the energy system here on the right hand side, connected through networks, and there is a kind of interconnection link. Now we have chosen a power socket here, but it's typically it is a smart meter, for example. And then we have local generation at the site of the household, which could be a micro CHP plant or, for example, a PV plant. But we also have different types of household appliances. And the idea is to get the whole system better coordinated, and to make a household and the appliances which are present in the household part of an intelligent energy system. Now, what could that mean in practice? So 3 examples how the Smart A vision could look like, and actually this is a slide which we drew up when we applied for the project, and we did not change it in order to show also now at the end of the project what was our vision in the beginning. So you could imagine that a freezer in a household receives a signal from local electricity operator that a load peak is expected at a certain point in time. And the freezer is smart enough to store cold in the morning and to try to avoid the operation of the compressor of the freezer during the peak time. So that would be one option. Or another option would be that a consumer walks up to his dishwasher, loads the dishes in, and leaves for work. And he sets the appliance, the dishwasher, in a ready-to-start mode, which could then be used by the electricity system, or in this case also by the heat supply system if it's connected to a hot water system. So as soon as enough energy, for example hot water, is available, the appliance will start and use solar energy as a hot water supply. And the third example is a washing machine, which is quite smart, or very smart, and checks the weather forecast from the internet and makes some calculations and gives a signal to the consumer that there will be a sunny day today, so maybe you would like to load a higher temperature cycle clothes into the washing machine and let it be in standby operation to use this solar energy. So these of course are quite bold visions, and you could cluster them into a fully automatic operation, which would be the first option. There is no consumer interaction required. You could have some form of low-level consumer interaction where you actually ask the consumer to set the appliance in a ready-to-operate mode, and then the operation can be triggered by an external signal. Or you could have very complex consumer interaction, which, well, I would say personally, and also at the end of 2.5 years of work in this project, I would say might be too ambitious, at least for the next decade or so. So let's have some visions, but let's look into more realistic scenarios, and that could be maybe the first two of those on this slide here. Now, our colleagues of the University of Bonn in Germany have been doing a huge workload in collecting information about the typical usage patterns of household appliances. What you see here is not the picture of any individual household. It is rather a very generic household, which the information which you see here is more the probability of an individual appliance being operated at a certain point in time on an average European day. So you can see here there is air conditioners ongoing, but there's also a circulation pump from a heating system ongoing. So it is a kind of mixture between a summer and a winter day. You can see here that, for example, the water heaters on top, they have a quite high energy consumption in the evening. That is, for example, when people do the washing or when people take a shower. Whereas air conditioners are typically being in operation in the later afternoon when the outside air temperature becomes high and you need to cool down buildings. And you have some appliances which you probably are not able to shift. For example, if you want a hot meal during noon, then you would not like to defer your lunch. But there are other appliances which could quite easily be shifted, like tumble dryers here. They tend to be used in the evening hours when people are back home from work. They do some washing and then they do the tumble drying. And there are also dishwashers, which are typically more used in the evening. After the dinner, people load the dishwashers. So this is giving us a picture at what times of the day we might be able to use load management options with smart appliances. Now, again, a second piece of work of our colleagues from University of Bonn and also Miele was to look at what kind of options do we have in order to shift the electric load which appliances are taking. And basically we have looked at two options which you could use. One option is the smart timing of the appliance cycle. So the question is, when does the appliance actually start? Now, many electric appliances already have a timer function where if you switch the appliance on, you can choose, for example, the appliance should start in 2 or 3 hours, or maybe more advanced appliances, they have a function to let you choose that in 8 hours when you return from work you would like to have the cycle finished. Now, of course, you could make it more flexible and say, well, I'm returning in 8 hours from now, so whenever the appliance is running, I don't care. So what are the technical options here? Washing machine and dryers, they could technically be shifted quite a long time, but based on the consumer research which we did, we found that most consumers do not like the idea of wet clothes laying in the washing machine for quite a long time. So therefore, the theoretical maximum of 9 hours is in practice reduced to something below 3 hours, which is typically the time when people are available for taking clothes out of the washing machine, either in the morning or in the evening. Dishwashers is a better appliance in terms of load shifting because people are quite used to use a timer function here. Typically we expect that they could be shifted up to 6 hours. The maximum would be even more than 12 hours. You could charge it in the morning and maybe it's just operating the next night. But typically would expect about 6 hours as a maximum for shifting dishwashers. I'm not going through all the lines, you can read it out yourself. The second option is the interruption of the appliance cycle. So here we look at an appliance which is already operating, and that of course also applies to appliances which are always operating, like the refrigerators and freezers, which are automatically operating. So we have looked at what are the technical constraints and what are the constraints from consumers in interrupting the appliance cycles. Now, washing machines, for example, they typically have hot cycles, and in a hot cycle it doesn't make much sense to stop the operation for an hour or so, because then the tub will cool down and you will have to heat it up again. We would have a lot of energy losses. But with dryers it's a bit different, because dryers do not have such a high energy content in the clothes which you're having in the compartment, so it is easier to stop them for operation for about 30 minutes or so. Refrigerators and freezers, they will start they are able to stop their operation if they can anticipate this by cooling down their compartment maybe a little bit more than typical, and then avoid the operation of a compressor typically for 15 minutes or so, and then they have to start again. Of course, this only applies if the user does not leave the door open. Now, we have also looked at the consumer objections and wishes. I have already mentioned this. We had a quite intensive consumer research looking at methodologies like questionnaires, focus groups, and also in-depth phone interviews. And what we found are a lot of objections which people have, and what are people afraid of. Now, there is first of all, we see that smart appliances have additional costs. So we have to bury the additional costs, and the question is, who will pay the additional cost of a smart appliance which has additional technical features. Consumers want to be able to retain the full control, so they do not like the idea that an electric utility is controlling whether the washing machine is running or not. Or to put it in concrete terms, they must be able, or they want to be able, to override any external control or automatic method of functioning. So in order to give them trust and confidence, it would be good to give them the option to override any smart operation if they think this is required. There are some health and safety issues. Of course, the service quality should not be compromised, both from refrigerators, freezers, but also tumble dryers, washing machines, etc. So they need to deliver the service. And of course, an appliance which is set in a ready to operation mode should not be setting the apartment on fire in the meantime. So there is a security issue, safety issue, which we need to address. There are doubts about the maturity of the technology. Will it really work, and will it deliver the benefits which we are expecting? And there's also a skepticism whether there will be ecological effects. Now, the outset of the project was that we tried to increase the ability of the energy system to absorb wind power in a higher share, looking at the overall installed generation capacity. Now, consumers in principle tend to accept this idea, and they are willing to contribute, but they're not sure whether it would really work. Now, what are the wishes of consumers to get smart appliances going? In order to compensate the higher investment cost, of course, we will need some economic incentives. I will come back to that later in a minute. But we also need to provide enhanced safety functions to give the consumer more trust in this more complex appliance. So any additional comfort which we can give to the consumer will help the consumer to accept the smart functionality. Enhanced comfort and usability, I said this already. High quality service and support. If something does not work as expected, smart appliances manufacturers should provide a very good service and support so that consumers do not have to be worried about their appliance being broken down for quite a long time. And it doesn't hurt if the smart appliance also has an attractive design. Now, going back to the a little bit to the theory or to the principles of demand response and load management in energy systems. This is a clipping from an article from 2006, which is showing some principles of how demand response can be used to change the load curve in the energy system. And most typically, people are looking at load shifting, which is clipping peaks and filling valleys at the same time. And historically, this was the objective of the energy industry, to have a flat load curve. That was the key objective, because then you could run most power plants at full load, and that would be the optimal utilization of the existing infrastructure, including the networks. Now things are changing. And looking at a system with a high share of renewable energy in the electricity system, we must be able to have a smart system. And the smart system actually means a change of paradigm. We do not talk about the optimal load as being flat. We talk about the optimal load of being flexible. meaning the load is meant to be able to respond to changes in the provision of electricity from fluctuating resources like solar energy or wind. So the challenge in the future will be to balance out variable wind and solar generation. And this means not scheduling the load management. It rather can also mean that we have to balance out the short-term imbalances which we are facing from wind generation. So we have, for example, a forecast of the wind production, say 4 hours in advance or 2 hours in advance, but the actual production will deviate from that. And the key value, that is the key assumption of our project, is the key value which smart appliances can bring in a system with high shares of wind and solar energy. The key value is by contributing to the balancing of this solar and wind generation. Now, let us now turn to the modeling results, and this is now going into the economic benefits of smart appliances, giving the framework of high shares of wind and also solar energy. And the first of 3 steps which we did here is to take several approaches to determining the value of demand response devices which you can use for balancing out imbalances in the system due to wind generation. Now this is just a clipping of a model run, and you can see here that we have been looking in our models at a system with a peak load of about 15 gigawatts, so it is a small sized country maybe. And you can also see here the blue line, that is the original load curve, and the red line, that is the load curve, how it was modified using appliances in our computer model. We have determined how appliances can be used to optimize the uptake of wind. And you can see here that we are not talking about only clipping peaks. Here is an example where a peak has been clipped a little bit, and you can see here, we could say this is a filling of a valley. But there are other points in time, for example here, where you can see that an artificial peak has been generated, and this is an indicator that we had extra wind, more wind than we had expected, and then we had tried to switch on additional demand and to kind of either postpone demand from earlier times or schedule demand before it would originally happen in order to make use of the additional wind and not requiring, for example, to switch off wind power plants because there's no demand. So this is just an illustration of how the work looked like. Now let's try to understand what the key effects are, and it is important to reiterate that we do not talk about scheduling of appliances, meaning using them as a resource in power plant scheduling, maybe a year ahead or a week ahead or so. No, we only looked here in this study, at least in this analysis here, we looked at the quantitative results or benefits if we use smart appliances as a resource of balancing power. Now, if we do that, if we introduce smart appliances or other demand response options into system balancing, and we have high shares of wind, there are 2 major effects which we can see. And the first one is that we reduce the requirement for spinning reserve in the system. Typically, if you have high shares of wind, you need to have an adequate share of fossil energy, part-loaded fossil energy power plants, which are running as so-called spinning reserve, in order to be able to react quickly if there is a reduction in the wind generation. And in order to ensure stability of the system, you need quite significant shares of these part-loaded spinning reserve. Now these fossil plants, they are running in a suboptimal mode because they are only partly loaded, so they have a lower efficiency and higher CO2 emissions as if they would be operating at full load. And the second effect is that we are able to avoid situations in countries or regions or countries or regions where we have very high shares of wind, you run more often into situations that you do not have sufficient load, sufficient demand to actually use all the wind which is offered. So the more wind we have in the system, the more often we run into situations that we have to switch off windmills, although they would be able to produce. So we try to avoid the wind spill by making the demand more flexible and making use of this. Now, both the effects, reducing the requirements of spinning reserve and reducing the wind spill, they both lead into a reduced use of fossil fuel, because typically balancing power plants are fossil power plants, and the marginal power plants, if we have to switch off wind energy, then typically a fossil power plant has to take over. And of course this also leads to a reduction of CO2 emissions. Now, on the right hand side you see some results of this of our calculations. So I'm making a big leap now to the results of a long series of calculations. So here we have a country with a 30% wind share installed generation, and we have actually three types of countries. We differentiate between countries with a high flexibility generation system. For example, this could be a Scandinavian country or country in the European Alps. In this case you have a relatively low value from demand response if you have a high share of wind as well, because the flexible system with a lot of hydropower plants is already able to accommodate the flexibility and to react on changes, on sudden changes in the wind generation. So introduction of demand response does not add so much benefit to the system, because the system is already quite flexible. Now, the opposite would be low flexibility countries, which are characterized by a high share of quite inflexible fossil or even nuclear power plants, which are very difficult to regulate. And for example, Germany or France or Poland would be European examples for these kind of countries. And you can see here there's a big difference between the two. Low flexibility generation systems can provide quite high benefits for DSM. Now, the units, I did not explain it. The unit which we have been using here is, we assume that we have 1 kilowatt of demand response load which we can use, like we can use it for an appliance, and this was shifted by 3 hours. That was the option which we used. And the question is now, what is the value in the system? And the modeling results you can see here. In low flexibility countries, the value can be in the range of 90 euros per kilowatt and year, and in high flexibility countries the value is down to some 20 euros per kilowatt and year. What that means for appliances we will see in a minute. Now, this might be a little bit confusing or difficult graph to grasp. Maybe you might want to go back later after this presentation and look it up again. This is now a transposition of what you have just seen down to the 29 countries, the 29 European countries which are typically in the focus of European studies, that is the current EU members plus Norway and Switzerland. And just to point out a few examples, well, to explain you here, we have looked at the year 2010 and the framework conditions in 2010, looking at the current wind shares, for example, moderate energy prices. We have looked at a scenario for 2025 with two different energy price scenarios. So the lower price scenario is looking at some 25 euros per megawatt hour of fossil fuel cost, whereas the higher price scenario, which is the green bar here, is looking at some 35 euros per megawatt hour of fossil fuel. And there's also a differentiation in CO2 costs between 20 and some 45 euros per emission allowance, meaning per ton of CO2. Now, let's look at a quite significant example here. Norway is a country with a very high share of hydro generation, and looking at the balancing of wind power, there is hardly any benefit from a demand response, because the system is so flexible that it does not need additional demand response. And looking at other extremes, well, Sweden, for example, is more or less a similar case, although we already can at least see some bars here. Austria on the left-hand side is also very low value country, and also Switzerland. So all these countries with a very high share of hydropower. Now, The star here in the analysis is Denmark, which is also a Scandinavian country, but they have a completely different generation mix, which is largely fossil, a lot of cogeneration power plants, and you can see here that the benefit for 1 kilowatt of VSM load is going up to some 130 euros per kilowatt in the year 2025. Now you can see there is a big difference between different countries, and the main driving factors is the flexibility of the generation system and the share of wind power which you can expect in 2025. Look at Great Britain, for example. Here again, currently there's not a big value because the wind share is not that high at the moment, but we expect a very steep increase until 2025, and then there will be a very high value for demand response option. I have to speed up a little bit, so I will try to run through the next slides a little bit faster. This was a different mode of, or a completely different modeling run, where we did not look at different countries, but we looked at different appliances. And we chose 3 different appliances, which is a plain washing machine, a typical dishwasher, and a combination of a washing machine and a dryer, which we call the washer dryer. This is a technology which is not very common, but which would have quite high value, as you can see here already in the graph on the right hand side. Now the research has shown that if we compare different appliances, which one has the highest benefit under the same framework condition. And you can see there are 2 drivers. The first driver is the degree of flexibility which the appliance offers, which in fact means how long can we shift. If you recall from one of the previous slides, I have said that if you interrupt a refrigerator or a freezer, then it can be up to 15 minutes, and then we run the risk of compromising the food which is inside, so that then we have to operate the compressor again. Whereas the dishwasher can be delayed up to 6 hours or maybe even longer, and you can see that exactly here, that the dishwasher has a relatively high value. And the other element of giving value to individual appliances is the volume of energy shifted. So what is the average load during a cycle, and how much kilowatt hours can we shift, or how much decimals of a kilowatt hour can we shift along the time. And here the washer dryer is very interesting, because the washer dryer allows us both to shift energy for a much longer time than with the washing machine, because we are drying the clothes immediately after the washing, so there's no concern of leaving wet clothes in the washer. And we are also talking about a higher volume of energy, because the total cycle is 2 hours, is 4 hours instead of 2 hours, and that makes a lot of difference. Okay, now the next step would be checking the cost of how can we enable smart appliances, and what does it cost us. And we have looked at different cost elements. What activities do we need to undertake to make smart appliances going? Now, the following cost items did we look at, or did we integrate into the calculation? We have additional production costs for smart appliances. Modern advanced domestic appliances, they are typically already equipped with an electronic controller, so it is not that we need to add intelligence to the appliance, it's rather that we need to add a communication module. So typically we have a power line communication module, for example, or a wireless LAN communication module. Here we have some significant cost in the first units which we are producing, but we expect a very significant reduction through mass production, which we might have achieved already in 2025 or afterwards. The second element is that we need an in-house communication hub in order to send signals to appliances, and if there's a two-way communication, also to receive signals. Now, at the moment, you might need to install a very specific smart meter plus a communication gateway, but in the future you could also imagine that this communication function is taken over by any wireless LAN system which many consumers will have in their household as well. So there might be no additional cost in many households in the future, but currently it might require an additional investment. And then we have to say this, and this needs to be taken into account, smart appliances means that appliances are in standby operation for a longer time than it was the case previously. We expect that we have about 1 watt of load for a smart appliance waiting to be called into operation, and that of course means additional electricity consumption that needs to be paid for. We did not look at the cost of smart meters because actually we don't need them for all the smart appliances operation. There are many business cases which you could imagine where you don't need an intelligent energy meter. You need a communication module, but not necessarily a smart meter. And we also assume that smart meters will be provided in order to give other services to consumers, for example, transparency of electricity bills. So we have not included the cost of smart meters. Now, let me jump immediately to a comparison of the cost and benefits. And here you see the picture which you have seen before already. This is again the euros per kilowatt of demand-side management load for the different European countries, and you see again the high differences between countries like Denmark and countries like Norway. And the red box shows you the expected range of costs for providing 1 kilowatt of demand response load from domestic appliances, and this is for the year 2025. So we assume that we enter into the mass production of smart appliances, but still, depending on the framework condition, depending on the electricity price and other factors, we expect, say, between 10 and 30 euros per kilowatt and year of demand-side management load, which we need to spend. Now you can easily compare the bars giving the benefit and the lines giving the cost. So you can see, for example, if you look at Belgium, you can see that if we have the lower boundary of the cost and the lower boundary of the 2025 benefits, then we might be able to make a net profit, which is a difference between the two. And if we have the higher energy price scenario, then in Belgium we seem to be on the safe side. And there are many countries where you have definitely very good cases for smart appliances, like this would be the UK or Ireland, or say the Netherlands or Portugal. But there are also other countries, I pointed out already, Norway here, or Sweden, and other countries where we'll probably not reach the threshold of smart appliances becoming viable, at least not for balancing wind generation. Now, let me say a few words of caution regarding these results. These figures all look quite nice, and they seem to be very exact. Now, the analysis, let me start with the second bullet point here. The analysis which we done was based on quite a number of rough assessments. So please do not count any digits behind the comma. It is really rather giving you the orders of magnitudes or rough estimates of costs and also of benefits of smart appliances. So there are uncertainties, and the results should be treated with some caution. But on the other hand, there are also additional benefits which smart appliances can deliver, and we have not looked at them in our modeling in this project. As I said, we only looked at balancing out wind power, and there are additional benefits like, for example, if you are able to manage congestions in local or regional electricity networks. Just to give you an example, I showed you the very low figures for the balancing purpose of demand response in Norway or in Sweden, but we do know that in the Nordic countries in Europe we do have a problem in the transmission lines, because the generation, the hydropower, is typically concentrated in the north of the country, whereas the consumption is concentrated in the south, where the industry is located. So the lines are congested, and we need to build new lines in order to manage just the peak load during a few hours of the day or of the year. So here smart appliances could help, even in countries like Norway or Sweden. And it's also worth mentioning that the analysis is performed on a country-by-country basis, so we have looked at individual countries. Now currently the balancing of wind, or generally the system balancing, is being done mostly on a country-by-country basis. Within Germany it's even 4 different balancing regions. Now, to the extent that the balancing markets gets integrated in Europe, and the same applies of course for other parts of the world, then the differences between the countries will be reduced. Okay. Now that's already one of the final slides here, the pre-final slide. We have different actors, and I'm just running through them very quickly to leave some time for discussion. So far we have looked at from a bird's eye perspective on the whole system, but it's much more complex in practice, because we have different actors. We have manufacturers of appliances. They have extra cost in producing the appliances. They will give them to retailers. They have to sell it at a higher retail price. Smart households will probably have to pay this higher price in order to get the appliance installed. In order to bring smart appliances on the market, we probably need aggregators which are able to combine the benefits of, say, 1 million of households and their appliances, and to bring them on the market for system balancing or on a power spot market. And then we have retailers of the smart households, and we have other energy consumers. Now, if we look at who has a benefit, we just did that on a very qualitative basis. The smart households, first of all, have to bear extra costs, so they have a disadvantage, which is meant in red, which is indicated in red here. The system balancing will reduce their overall cost, but on the expense of the other balancing power providers in the fossil power plants, which will be driven out of the balancing power market. And typically, reduced cost in system balancing will lead to an overall lower use of system charge or tariff of the transmission system, and this means that all the retailers and in the end all consumers will have a benefit. Now, the key message here is, if we introduce smart appliances, then under the current framework condition, and if we do not change the default allocation of values and of benefits, all energy consumers will profit, including the aluminum mill and including the big cement industry. But the smart household has to bear the cost. Of course, that's not fair, and this is why we have to find ways of incentivizing the smart appliances, which basically means we need to transfer money. For example, the smart appliances aggregator, he will earn some money on the system balancing market, so he will be able to compensate the smart appliance, the smart household with the smart appliances, with giving him some money. And also the retailers, they might be able to give incentives or premiums to the users of smart appliances, or offer flexible tariffs which reward the smart operation and the intelligent management of load. Now, as a conclusion, just very quickly, smart appliances offer quite a variety of load management options, but we have restrictions looking at the technical capabilities of the appliances and also the consumer preferences, which in the end might kill all technical concepts if we do not follow or if we do not understand consumer preferences. The consumers were in principle quite happy, but they have requirements that they do not want to change their daily routines, and they want to have comfort and safety maintained. And if we look at the system perspective, the value of a smart appliance is driven by the flexibility of the conventional generation system in a country or in a region, and also the share of wind and solar energy in this generation system. And then typical values for smart appliances for balancing wind power generation are moderate. So we're not talking about hundreds of euros which we could spend every year. It's rather in the range of 6 or 10 or maybe 12 euros for an individual appliance. Not all the EU countries at the moment seem to offer really viable potentials for smart appliances, at least if we only look at balancing of wind generation. But smart appliances can, for example, have additional values, for example, when it comes to congestion management, as I explained with the example of the Nordic countries. And in the end, in order to get all this running, we need incentive mechanisms like flexible tariffs or direct subsidies to smart appliances in order to give the right signals to all the actors which are involved in the deployment of smart appliances. So that was it. Thank you very much for your attention.